Hello, everyone, and welcome to part 2 of chapter 10. We're going to be dealing with the muscle contraction, energetics, and then a few other things that we'll talk about. But that's kind of the big thing for today. So, how muscle contraction happens. So, what we're going to start with is excitation contraction coupling, which we talked very briefly about. And the excitation contraction coupling is how we're going to link what happens with the neuromuscular junction and how muscle contraction happens between the action potential that happens on a muscle fiber, the excitation, and the start of a muscle contraction. How does that happen? Now, very important, this happens near triads because that's where the action potential goes down the T-tubule into the terminal cisternae that dumps the calcium from the terminal cisternae. Okay, now we drew that out last class. So if you guys have practiced with that a few times, now let's look at what happens when we apply that knowledge. Now, based on that drawing, if you're looking at it now, and if you have it drawn out, go ahead and grab it and look at it as I say this. Is that now I like to think of it like this. Let's imagine that calcium is like a dangerous prisoner. Okay. And the terminal cisternae is the prison, okay? Now, if you were to find out this dangerous prisoner has escaped prison, then you're going to be very tense. You're going to be very tense and tied up because you're worried that they might come in and they might, you might get hurt by them. And then you find out they've been arrested, they've been put back in prison, and you breathe a sigh of relief. When calcium is high in the terminal cisternae, a muscle is relaxed. And when calcium is low in the terminal cisternae, a muscle is contracting. Okay? Definitely know that. That's going to help you guys understand what's going on here. That's kind of the keys to the city, so to speak, but understand why. Understand why those statements are true. Okay? Why they are. Now, so I'm going to help you understand how a muscle contracts. Okay? Then we're going to walk through it. Now, let's kind of imagine it like a date. Okay, we have myosin who wants to hold hands with actin. Actin has an active site that myosin wants to bind to. Troponin-tropomyosin complex is like daddy who doesn't want myosin to hold hands with his daughter. Mama calcium, she's going to be in the kitchen and she's going to be in the terminal cisternae and she's going to be she can control daddy and move daddy the way she wants him, but she's in the kitchen right now. Maybe she's making some coffee for him. She's getting a snack because they're all going to meet. So daddy is talking to the man. And mama calcium, she sees daddy doing this. So mama calcium comes out of the terminal cisternae and she gets a hold of daddy. And what she's going to do is move him out of the way. And then myosin's going to move in and bind to the active site, okay? And that's what we're going to see happen. Okay, and that's going to cause a muscle to cross bridge and then contract. Then calcium is going to drop back. This is going to go back, and troponin-tropomyosin complex is going to be inhibiting actin and myosin again. Okay, so this is what calcium does. It's very important that we understand the role of calcium in muscle contraction. So let's take a look at this. So the thing we want to really understand is daddy, troponin-tropomyosin complex, is going to be like daddy, protecting his daughter so that myosin doesn't hold her hand. Okay. Now, the zone of overlap is right beneath the terminal cisternae. So when calcium dumps out, it goes right to the zone of overlap and immediately causes a contraction. What happens is mama calcium comes out and she gets a hold of daddy. She goes to troponin C, and tropomyosin moves out of the way. And what happens is troponin-tropomyosin complex, is no longer inhibiting myosin and actin. So now the active site is exposed. Myosin will then bind to the cross bridge. It will cross bridge. Myosin will bind to the active site of G-actin, and then a muscle contraction can occur. Let me explain how it happens. Let me help you understand it. So what we're going to show you here is, this is that date I was giving you. Mama's in the kitchen, mama calcium, she's in the sarcoplasmic reticulum, she's in the terminal cisternae, okay? Now, the young man myosin wants to hold hands with actin. Daddy, troponin-tropomyosin, won't let this happen. Mama calcium comes out of the kitchen and says, daddy, come over here and help me. And daddy moves out of the way and exposes the active site. Myosin reaches out and cross bridges. Myosin reaches out and holds hands with her. Okay. Now myosin's holding her hand. When mama calcium goes away, that's going to go back, and we're going to be able to stop that. We're going to see how calcium really is important to regulate that. Very important that we understand that, okay? Now, what's going to happen is this calcium comes in, and that triggers the terminal cisternae to expose G-active active sites. Then what's going to happen is we're going to take myosin, who is highly charged. Myosin is highly charged, and it's going to cross bridge. Now, kind of think of it like this. Myosin wants to hold hands with actin. He's very nervous about it. He's going to reach out kind of nervously. And when he does, he's full of that energy. He's a high energy conformation that he's in. So as soon as he binds, he will pull her in close and give her a kiss. And that's a power stroke. The myosin head binds and it moves, and it's powered by ATP. Now that ATP makes the myosin heads contract. Now these myosin heads are stuck. They're stuck and fused to the G-actin's active sites. So myosin will be given to disconnect the cross bridge. Once that happens, that breaks the cross bridge, and then what happens, it re-energizes it. It puts myosin back to a high-energy conformation, so it can contract again. Then calcium goes back into the sarcoplasmic reticulum. That means tropomyosin goes back to covering the active sites of G-actin are covered, and the muscle relaxes. Okay, so let's take a look at it. So right here we have a thin filament. We have G-actin with its active sites, and we have tropomyosin and troponin C. Okay, we have myosin heads in their high energy conformation on myosin. These heads are loaded with ATP. They're full of nervous energy for their date. They come into their date to meet myosin, and they meet her dad, and her dad's like, what do you intend towards my daughter? I've got 5 acres and a shovel. Nobody will miss you. So what's going to happen is mama calcium comes out and she binds to troponin C, and that moves out of the way. Troponin and tropomyosin now are no longer blocking the active sites. So myosin, who's high energy, is going to reach out and form a cross bridge. Now it's loaded with ATP energy. So this ATP energy, what that's going to do, as soon as it cross bridges, you will form a power stroke, and that will break down ATP. ATP is literally hydrolyzed here, and the ATP is consumed for that power stroke to happen. So what has to happen? We have to give ATP to the myosin heads to break the cross bridge. Okay. And then calcium goes, that starts to cause a relaxation. Calcium goes away, and troponin tropomyosin complex goes back to blocking the G-actins. Okay. All right. So I hope that makes sense. And here's an image showing you in a more complex way what the textbook shows. Okay. All right, so that's how that happens in step-by-step form. One step, next, okay? You definitely got to understand this as a concept. I'm going to ask questions about it that get to the understanding of it, so definitely do that. Now, when a muscle contracts, when this process happens, the ends of a muscle move towards the center. If we lock one down, like the origin, the point of attachment that does not move when the muscle changes position. And we have a free end, the insertion, that moves towards the origin. So this will cause one end to not move, one end moves when you lock it down to a non-mobile end. Okay, that's how origins insertions work. Now, how does relaxation happen? Relaxation happens, guys, by taking 3 things that we can control. We can control how often I tell a muscle to contract, the period of neural stimulation. We're going to see the enzyme acetylcholine esterase is involved to break down acetylcholine at the neuromuscular junction. We're going to see how much calcium we have affects how long a muscle can contract, and how much ATP is available. Now, normally we're going to have enough ATP to make muscles contract, but we can run out of some ATP. The muscles get fatigued, they get tired, they run out of energy, we didn't have enough to eat, and the muscles get weak. That's why we get really weak when we get very hungry, and we stop being able to make muscles work when we get really, really hungry, okay? starvation level. Okay. Now, relaxation, there are three things. Acetylcholine esterase is going to break down acetylcholine at the neuromuscular junction. When it does, it breaks it down into two chemicals, acetate and choline. Now, the choline gets reabsorbed and the acetate just floats away. ATP binds to your myosin heads and breaks cross bridge. That's going to cause a relaxation. And calcium levels drop in the sarcoplasm. Now, ATP binds the myosin head, break the cross bridge for a muscle relaxation. This is why we go into rigor mortis soon after death, is that we die, we don't make any more ATP. We can't break the cross bridges, so the muscles go into rigor a little bit after death, a little while after death, not immediately after death. You go into rigor a little while. Rigor is kind of a little while after death, after the body has really ran out of ATP, though some of the tissues are still somewhat trying to have some chemistry going on, some cellular processes. It's out of oxygen, but some of these tissues are starting to and then they'll break down and degrade and things like that. Okay. All right. So that's what we're going to cause. So to cause the muscle to contract, we have an action potential comes into the neuron that opens up calcium channels, and calcium diffuses in. That causes the exocytosis of acetylcholine. That binds the nicotinic acetylcholine receptors on the motor end plate. That depolarizes the muscle cell. The depolarization goes down a T-tubule where we cause the release of calcium from terminal cisternae. That causes a muscle contraction. And then what we do to relax, we break down acetylcholine. We also take the calcium and bring it back into terminal cisternae. We use ATP to break the cross bridge and a muscle relax. All right. And this is how an animation, how a muscle actually does, how neuron depolarizes the skeletal muscle cell, travels down T-tubules, causes calcium to dump out of the terminal cisternae, causes a muscle to contract. Okay. It does a really good job of showing that. All right. Now, one of the things I want to talk about as well with muscle physiology is that when muscles contract, there is something called the all or none principle, and we're going to talk about that. But one of the things is going to be the number of cross bridges. Now, this is something you be blessed with genetically. Some people, a smaller person, may have more cross bridges, more myosin heads that can cross bridge with G-actins than somebody just a little bit bigger. But usually as you get bigger, you get stronger because you get more cross bridges. The strength, the amount of tension a muscle can produce is directly dependent on how many cross bridges it can form. That's why you get stronger when the muscle gets bigger. But some people are just going to have more to begin with. So they are stronger than they would look to be. Okay. Now, when calcium is released, one of the big things is it goes through the whole muscle. So the whole muscle cell contracts or it doesn't. It contracts all the way or none the way. There is no half-hearted muscle contraction. Now, we can have just a few muscle fibers contract, give us a very weak contraction for the whole muscle, or every muscle fiber contract in the muscle and give us a much more powerful contraction, or somewhere in between and give us an in-between contraction. But it always depends on how many cross bridges per muscle fiber, how many cross bridges per muscle. The more muscle fibers we get involved, the more tension we can produce. Okay. Now, the other thing that we need to understand is there is the amount of tension can also be the length-tension relationship. I'm going to talk about that. Very important when you get into heart physiology as well. If you guys do any pathologies of myopathies of the heart, ever talk about Starling's forces, length-tension relationship is very important there. The frequency of stimulation, how rapidly you can stimulate a muscle fiber, and how many muscle fibers I can stimulate. Now that's the thing, all of these things can be adjusted. Let's start with length-tension relationship. Now the length-tension relationship is basically saying this. You're going to produce the most tension if you stimulate a muscle when its sarcomere is at the optimal length. Greatest tension can be produced when the sarcomere is the optimal length. Now if we look at it, it's a little bit pulled apart. Okay? Where there's a lot of cross bridges that can happen, this will produce the most tension. Here we spread it apart too much. Now, let's say I took my arm, and I'm not a very big guy. Some of you might be some big dudes in the class. Sometimes I have some big, big strong guys in the class, and I'm not a very big guy. My fighting weight's about 160, not even my fighting weight, but that's like the weight I really strive to be. I sometimes flat around 170 to 180, depending on how many hot wings I eat the month. But the thing is, if you take your arm and pull it back, like you're going to punch me, and it's pulled back behind you, and I push against it, you're going to have a hard time overcoming my force. It's going to be a lot harder because you pulled the sarcomeres apart. When the sarcomeres pull apart, there's less cross bridging, so it's not going to form optimal tension. Here, it's been pulled out. It can't form tension. Here, it's squeezed in too close. It can't form any tension. Here, there's a lot of cross bridging, but there's not much room to move. Optimal spacing. So, the length-tension relationship. The number of cross bridges determines how much tension is produced. The number of cross bridges determines how much overlap between thick and thin. If it's stretched too far or compressed too close, it cannot produce adequate tension. When it is at its perfect length, it will produce the most perfect amount of tension that it can produce. Okay? Our heart gets into this too. Okay? Now, muscle twitches. Let's talk about that because we're going to get into messing with neural stimulation. So to understand, though, us messing with neural stimulation, we've got to understand, guys, a muscle twitch. A muscle twitch is a contraction relaxation. It is me flexing and extending. One cycle of contraction relaxation is a twitch. And I usually flex and extend real quick and say that's a muscle twitch, okay? Now, muscle twitches have three phases. There's a latent phase, and that's the gap between a neuron says fire till calcium dumps out terminal cisternae. There is a brief milliseconds of a period of time where the latent period happens in a brief fraction of a second of milliseconds, okay? Milliseconds. So a stimulus happens, and there's a gap between when the neuron tells it to work and action is formed, and the calcium dumps out of the terminal cisternae. Then there's a contraction phase, and that's when the tension starts to produce and get to its maximum. Then we produce our maximum tension. Then we go into a relaxation phase where muscle relaxes, okay? Relaxation phase is contraction phase when calcium goes up in the goes up in the sarcoplasm, and the cross bridges are forming, and all the muscle contraction, power stroke, and all that. When calcium levels drop in the sarcoplasm, that's going to cause a relaxation phase. Okay. Now, let's look at how we can modify that, because remember, this is one of the ways frequency stimulation can determine how much tension. One of these, it doesn't produce very much tension, but each time a muscle is stimulated immediately after a relaxation phase, there is a next contraction has a little bit more tension and almost a stair step till it gets to a maximum that's not very strong. This is called TRAPE. Okay. Now, wave summation. Here's the thing. In wave summation, it's before the relaxation phase, so a second more powerful contraction happens. This adds the tension of the first contraction to the next, hence wave summation. Incomplete tetanus. Muscle is almost at peak contraction. It's stimulated again and again and again in rapid stimulation. Cycles of contraction and relaxation are allowed. There's a little bit of relaxation, but it's very brief. Complete tetanus, there is no relaxation. In a complete tetanus, it goes all the way to maximum tension and stays that way until there is a relaxation able to be. A lot of times this might be due to a poison or something. Terminal cisternae cannot reclaim calcium, so this is a big problem, okay? Now let's talk about how many muscle fibers we can get involved. To understand that, we need to understand motor units or myotomes. For some reason, some of the med-surg professors out there that teach nursing classes like to call them myotomes. Motor units, that is a muscle fiber and all of the, a neuron, sorry. You got one neuron and all the muscle fibers it controls. That's the way I like to define it. Our book says all the muscle fibers controlled by a single neuron. Or you could say a single neuron and all of its muscle fibers that it controls. Same thing, Okay. Now, if you got small motor units, you get fine movements like eye muscles, your extrinsic eye muscles, your rectus, your obliques. They only have 4 to 6 muscle fibers for every neuron, so they give fine movement. Larger things, like bigger movements, like your leg muscles and your quads and stuff, you have one neuron controls like 1,000 to 2,000 muscle fibers at one time. So here we have a purple, blue, and red neuron. The purple neuron controls the purple muscle fibers. The blue neuron controls the blue muscle fibers, and the red neuron controls the red muscle fibers. Each of those red, purple, blue is one motor unit. Now that motor nerve can control many muscle fibers in a muscle so that I can get all the muscle fibers involved or only a few muscle fibers involved in a fascicle. I can get, so like for example, I always like to say, hey, you can gently wipe a baby's nose or you can punch a bad guy right in the nose. And you can do about, almost the same kind of motion to go for the nose, but one of them is gentle, one of them is forceful. That's because I can get more than one muscle fiber involved, okay? Now, let's talk about different types of contraction. Let's talk isotonic and isometric. Iso means equal. Tonic means tension, equal tension. Tension is constant, but length changes. Now, let's say I have a muscle, and this muscle can only lift 10 pounds, and that's all that muscle can lift. 10 pounds is all it can lift. If I give it a 5-pound weight, that's half of what it can load. It will lift it with no problem. If I give it a 20-pound weight, that's twice what it can lift, and it will stretch out. An isotonic means tension is constant, but length does change. In a concentric, tension is greater than the load that it's resisting. That means the muscle shortens and it contracts. Concentric contracts. Eccentric, that's when the muscle tension is less than the resistance. For example, the muscle can only lift 10 pounds. I give it a 20-pound weight. It can't lift 20-pound weights. It drags the muscle to the ground. The muscle elongates. Okay, it stretches the muscle. Now, isometric, iso equal metric distance. The length of the muscle stays the same. This means that tension does not exceed resistance and the muscle stays steady. Okay? The muscle doesn't change any distance. This is what keeps us steady. This is what keeps you sitting upright in your desk right now. Okay? Now, how do we supply muscle to energy? How do we get energy to muscle? We need lots of ATP. Muscle contractions need lots of ATP. We need to power the sodium potassium ATPase pumps. We got to build power the cross bridge. We got to build a break the cross bridge. Power stroke. We got to power stroke. We got to break cross bridge. We got to be able to run the sodium potassium ATPase pumps. All that requires ATP. So muscles use a lot of ATP. Now, there are 3 sources. One of them is creatine phosphate. What creatine phosphate is an enzyme. Now, let me talk a little bit about creatine phosphate. I won't go too in-depth on it. Creatine phosphate kinase. Let's say I've got an enzyme right here, and this enzyme is creatine phosphate kinase. And we have a phosphate here. Okay. Actually, here we go. Let's do ADP. Let's make it a little bit better. And let's say we have creatine phosphate. What we're going to do is we're going to take this phosphate and give it here and make ATP. There we go. Let's get that a little bit more biochemistry. A little biochemistry there, okay? Creatine phosphate kinase is an enzyme that takes creatine phosphate, takes that phosphate off of it, gives it to ADP, and makes ATP. Okay, we know what ADP, adenosine diphosphate, is. Now, it's an enzyme called creatine phosphate kinase. It phosphorylates ADP to make ATP. Now, glycolysis, which we barely talked about in chapter 3, only makes 2 ATPs per glucose, so it produces very little. One of the things that will happen when we do glycolysis, if I don't have enough oxygen available, I will do lactic acid fermentation to make lactic acid as a waste product that I'll make. This lactic acid starts to cause muscle burn and things like that. The main way, the biggest way, by far the most ATP, is going to be aerobic metabolism or cellular respiration, where we use oxygen and glucose. We produce about 34 ATPs, 36 to 38 ATPs, some people will say. We might say close to 34 for a lot of tissues. Our book says 36 to 38. I always kind of say, hey, that's really actually based on E. coli. Now, we need oxygen for cellular respiration. So to get oxygen, we have an oxygen-binding protein called myoglobin. Myoglobin, now if you've ever eaten a rare steak and people say, oh, it's bloody, and it looks like blood on the plate. That's not blood. That's myoglobin, not hemoglobin. That's found in blood. Myoglobin, myo meaning muscle globin. It is in the muscle. That is the red protein in muscle that makes muscle red, is the myoglobin. Myoglobin sequesters or binds oxygen for the muscle to supply oxygen to the mitochondria of the muscle to cause a muscle contraction. Okay. So the muscle's mitochondria needs a lot of sources of energy. It can use fatty acids, it can use glucose, it can use glycogen to be broken down, it can use ATP that's already there, cellular respiration, glycolysis, creatine phosphate, all of that stuff, CP, creatine phosphate, all of this stuff can give us enough stuff to make ATP and give us ATP to cause a muscle contraction. These are all ways that we can get ATP. Okay. Now, when muscles start to work out, they will start to consume oxygen. This is called excess post-exercise oxygen consumption, or EPOC. This is after exercise or any other kind of exertion that I've done. Okay. Now, the body needs more oxygen than normal for its metabolic activity. Breathing rate goes up, breathing depth increases. I just talked about this in A&P2 today. When muscles can no longer perform, we call them fatigued. That can be I've depleted my metabolic reserves, I've consumed all my energy. I've damaged the muscle. The sarcolemma, the sarcoplasmic reticulum have been damaged. The pH has declined, the muscle's gotten acidic. And that affects calcium ion binding and other enzymes. It also affects hemoglobin activity as well. This is going to affect hemoglobin. And it's also just weary due to the acidity that we have when we get blood. pH gets low, a low blood pH, more acidic. And we get pain, it gets weary, and we want to quit. Okay. Now, muscle contraction does produce heat as a byproduct. So, for example, if you start to exercise, you warm your body up. If your body is cold, one of the things it will do is cause a rapid muscle contraction to some of your large muscle groups. And that rapid muscle contraction we call shivering will help try to give us some extra warmth. Okay. All right. Now, this will be on the test for sure, too. Should be on the test. If I'm missing, I'm going to check, make sure it is before our next exam next week. But fast twitch, slow twitch, and intermediate twitch, there are some differences in them. Now, I don't have you guys really worry about how fast, like really fast, like peak tension is fast is really all I want you guys to really know. I don't want you guys to know how fast. I don't really worry about that so much. But the characteristics of these. Okay. Most skeletal muscle fibers in the body are fast twitch. They do get about 0.01 seconds or less to produce peak tension. Now, one of the things about them is they're going to have a very large diameter, and because they're really big, they have a lot of myofibrils in them. They have a lot of glycogen in them, and they don't have very many mitochondria. So the muscles that are fast twitch, they produce powerful contractions because they have myofibrils, but fast twitch get tired fast. They wear out fast because they don't have many mitochondria, so they have those big and all those myofibrils, so they use ATP high, but they don't have much mitochondria to make ATP, and so they use anaerobic activity for prolonged activity, which is not very effective. Slow twitch, half the diameter of fast twitch fibers. They're slow. They're 3 times longer to produce tension after stimulation. They are good after fast twitch has become fatigued. Slow fibers have a high number of mitochondria, so that's going to keep aerobic metabolism going. They have a lot of networks, and they have a high oxygen supply. They have a lot of myoglobin. Okay. This is our slow twitch. This is our dark meat. Fast twitch is our white meat. Slow twitch is our dark meat. Okay. Dark red in appearance because our dark meat. Okay. Resting fibers have substantial oxygen reserves because they have all that myoglobin. Mitochondria make a lot of ATP as well. They contribute more ATP. The ATP demand is really reduced because there's not as many cross bridges. They're really slow. And it's less dependent on anaerobic. It needs aerobic. Slow twitch really want aerobic mechanisms, aerobic metabolism, cellular respiration. Intermediates between the two. It looks like fast fibers because it has a little bit of myoglobin, so it doesn't have very much myoglobin, so it looks more like a fast fiber. But they have an intermediate capillary network, and they are more fatigue resistant than a fast fiber is. Fast fibers, they're fast to work, they twitch fast, but they wear out fast. Okay. So you could tell the difference between like the dark meat and the white meat and what will happen is these will change due to your athletic training. Okay. All right. What causes muscle to bulk and tone? Growth hormone stimulates the growth of muscle. Testosterone stimulates muscle mass. Testosterone is usually what we mimic in any of the anabolic steroids. Muscle tone is called hypertrophy. Muscles get swole. They increase in diameter, not number. The muscle gets bigger. Atrophy is when the muscle gets weaker because I don't use it. Like I broke a limb and had to wear a cast and couldn't walk and use it very well. And then my muscles shrink. And then my one leg that was broken now looks skinnier than the other leg that I had. Okay. They atrophy. Now, just a little bit, I'm going to talk about cardiac muscle. Cardiac muscle, I remind my students in AP2 of this when I get to the heart. Cardiac muscle is involuntary striated. There are no T-tubules, so there's no triads. They don't have They have T-tubules, sorry. They don't have triads because they don't have terminal cisternae. That's what I meant to say. I apologize. I kind of stepped on it a little bit there. I'm getting a little tired. Now, they use aerobic energy, aerobic metabolism. They have intercalated discs to contract without neural stimulation. Smooth muscle lacks T-tubules, like sarcomeres, non-striated, involuntary non-striated. Okay. Now let's talk about muscle fascicles and arrangements, and then levers, and then we'll be done. Okay. Muscles are arranged in bundles called fascicles. These fascicles can be arranged in a muscle in 4 ways: parallelly, convergently, pinnately, and circularly. Let's look at them. Let's look at parallel. Parallel, it's really that easy. The muscle fascicles run parallel to the axis of the muscle, long axis, like your biceps brachii does. The fascicles run parallel. Convergent, they start at a broad base and converge onto a single small tendon. Broad area of coverage on a common tendon. They converge, like your pectoralis major. Pinnate, muscles are found at an angle. Think about a pennant that you would see for like a baseball team. It's a triangle-shaped thing, an angle. There's unipinnate. Muscles, fascicles are on one side of the tendon at an angle. Bipinnate, they're on both sides of the tendon at an angle. Multipinnate, the fascicles branch inside the muscle. The tendons are internal. Now you can actually see unipinnate, bipinnate, multipinnate. Okay. All right, muscle fascicles arrange in circles as well. We call them sphincters. They are circular shaped. They purse string, what we call them, like a drawstring on a trash bag, purse string. Now let's talk about levers. Levers, this is going to determine how the force, movement, and speed, and range of motion of a joint happen. There are 3 parts to every lever. There's a fulcrum, applied force, and a load, or the load is sometimes called resistance. The fulcrum is the fixed point where pivoting happens. The applied force is whatever the muscle is pulling, you pushing on the lever. The load or resistance is what the object is being lifted. Now, when we think about levers, they can be first class, second class, or third class. First class is a pry bar, second class is a wheelbarrow, and third class is a catapult. First class, pry bar, what we have is our fulcrum in the middle with our load and applied force at both ends. In a second class, fulcrum is in the front with the load between the applied force and the fulcrum. Here again in a third class, fulcrum is in the front, the applied force is between the load and the fulcrum. Okay? That's the definitions. I'm going to ask one of these on the test. Okay? All right, guys, we're done. I'll see you guys in the nervous system. Thank you.